see my screen? Dear participants, hello.
Yes, sir.
Yeah,
Yes,
we
sir.
are.
Yes,
Yes,
okay.
sir. We are able to
Okay,
see your
that's fine.
screen.
That's fine. That's fine. Thank you. Thank you. So, good evening to all. Actually, I really delighted to be here to give some presentations. So, one moment. Yes, that's fine. So, when Professor Saraswati asked me to give some presentations on fluorescent based detection of microfluidic and micro and nanoplastics. Yes, I am also interested in really how people deal with plastics in daily life. So let me explain that. First point, I will give, there are two lectures for me in this particular total DP, and one is microfluidic chips coupled fluorescent probes and size separation detection in micro and nanoplastics. And second one on 27th of this month, that is the industrial effluent and quantification, yes, intensification of the microplastics removal. Okay, now. So my presentation today is I divided into two parts. The part one and part two. In part one, I'm going to discuss a general information about the plastics and microplastics. And in the part two, actually, I would like to give you some general information about the microfluidics and how they useful to detect microplastics in solutions. So, and then in generally, we can say that one is it's a type of simple interaction and some informative presentation I would like to give you today, in particularly in the point of view of the industry, what exactly an industry people wants instead of that learning. So what we have to give for industry people, because there is a lot of gaps in between, which I have found that one in between academics and as well as in industrial research. So we have to fill that gap. So let me start from my first part of the presentation today. So now here there are some pictures can able to see that why plastics are problematic. Can anyone please? Why plastics are problematic? Are they really useful or problematic? Can anyone audible? Can you audible me clearly? Hello.
Yes, sir.
Yeah,
You
it
are
is
audible.
Yes. So please, can anyone why plastics are problematic? Anyone can read that one, no issue at all for that one. Okay. So
Couldn't degradable easily, sir.
okay. So look at here in this picture. This is particularly in India and Asian and other Asian countries. The plastic is very problematic. The reason is very simple. First, why we choose? We replace everything in our daily life. In today's life, our life, we can't able to imagine our life without plastic. So the problem is the same issue are as another problem. The only why we have chosen the plastic is the most important material of our life is only because of its durability and low cost availability. These 3 points, only these 3 parameters that made us to choose a plastic instead of all to replace everything from milk bottle to implants and in our body. Everything we replace with plastic. But there is a dark shade of the plastic uses, in particularly if we can't able to manage properly the waste of the plastic. This is a problem we are facing now. The actual problem is not arising from the using of the plastic or producing of the plastic, but the problem arising from the how we are managing the waste of the plastic. So here you can see that there are some pictures on that screen, you can able to see that in daily life, everyone, in particularly in India, we can able to see this. These all your images are collected from in Indian scenario only. The dump yards, wherever we can see that, everywhere we can find plastic wastage and debris. We can find that one. Now come to the point, another point. Now, KCC is very clear here. Is another picture. Here you can able to see that one. In recent years, the people find that 52 kgs of plastic they removed from their cow's stomach in Tamil Nadu region. It's not just happening, it's not only in Tamil Nadu. Wherever we go in India, wherever any corner in India, you can find this type of situations. Because animals, they doesn't know, they can't able to differentiate which is edible or which is not. They simply knows that the smells, the material of product, the food or whatever, they think that that is also the part of food. So they simply consume that one. But this is facing the problem animals is because of a human being. So we have failed, no doubt about it. Our governments and people. So we are completely failed. The poor management we are failed and very poor management of the plastic wastage in India. I can say that one. And I'll come to the point. Another point, why these plastics are durability. Already we had discussed about the durability point. And then where they are. If you ask that where they are, the plastic wastage or debris, they are everywhere. So totally where they are reaching, so finally they are reaching to the oceans, everything, oceans, and they are polluting water bodies, and they are polluting soils, or even the smell of wastage or whatever it may be, when they catch a fire, so that they're causing the air pollution, and then it's everything. So they are making us very miserable lives. I know that one. And then come to the point, what happens when they reach it into the environment? What happens to plastic? So here our topic is starts. The plastics, they are started to degrade slowly, and some plastics they got break down by lighting or some other operations, mechanical issues, whatever it may be. They started to reduce the size first before they are going to degrade completely. How small they can degrade, that is another major issue. They can degrade from some macro to nano level particles also, they can get degraded. So this is the major issue now we are going to face. Another major issue is not only the plastic wastage and poor management, beyond that, the people now again facing the potential health risks and environmental concerns because of this microplastics. Now come to the 2 points. Let me share a few points about that one. We can see that when approximately 14% of the plastic produced worldwide are collected for recycling. So this is a major reason, particularly in India-like countries. So we can't able to recycle total plastic which is produced in India. Next, coming to the point, what kind of health risks? Because of microplastics, as we seen in last slide, as I already have seen that one, that they break down and they form micro and nano plastics based on their size. And then not only the plastics, in terms of structure, the chemical structures, So while we using the plastics, we added many things to improve their strengths, their properties and colors, and many others. I mean, additives, we can say that one, and plasticizers, additives, they are another additional synthetic chemicals which are causing to the environmental pollution. Now come to the point, next one. And then economic and social costs is another major issue which we are facing now. In not only the simply throwing a plastic bag or plastic the waste bucket or whatever it may be, and simply throwing outside. So we are facing another big challenge is economic and social cost. What are they? Waste management burden, impact on tourism and fisheries and inequity, right? So there's a lot of still many countries people they think that India is a poor country. We are not hygiene. We are not hygiene because of this type of wherever we can see that we can't be able to clean our environment or keep clean in environment. This is a major issue. Even I was asked by many of my foreign colleagues when they visit India the same question: why Indians are very they can't able to manage properly and they are not in hygienic. This always I used to face this question. I don't know the real answer, how to answer to them. And then what are the other scientific challenges? Let's come to the next point: detection and tracking and recycling limitations. This is the main, this is the 3 points. So when we come to the scientific challenges in front of us, and detection and tracking. These two are very big problematic, very big challenging issues for macro and nanoplastics particularly. Because it's not easy, we will discuss in coming slides what the impact of that to micro and nanoplastics. Now come to this one. Here you can able to see the picture in this picture. There are a lot of you can find the small pieces which you can able to see with visible. If they all are visible to us, so we can say that when these particles are micro or meso size in size, but we can't. There are beyond this meso sized particles. We can able to see with the microscopes smaller than this plastic particles which we cannot able to observe with eye. Now come to the point. So what exactly in general properties, if you come to the micro nanoparticles, we can say that one plastics, we can say that one it's up to 1 micron, 5 millimeters to up to 1 micron, they classified as a microplastic. And nanoplastics below that 1 micron. So we can say that and up to 1 nanometer, we can say that one. So there is no, actually, there is a lot of debate in size of the particular this nanoplastics. So I can say that one, there is we no need to keep a boundary line for the size of the nanoplastics because they can go any kind size of as low as much as low up to 10 to 1 nanometer also. And then shape, if you come to the shape, this is another bit, this is a major challenge here. This shape, we can't able to categorize even the micro and nanoplastics based on their size or shape. We can find those meaning. And then other additives and contaminants. So that's again how to consider is not only the plastic. Now come to the next slide. Here you can see that once. In this slide, you can see that. So the size below one, they simply 1 meter and 2.5 macro, meso, micro, and nano. We can able to see here. We can see that's some images. These are not some that images. I think images. You can see the microplastics. They're aggregated in that lost side in the nanoplastics. They have a tendency to aggregate easily since their size is very less and the surface uh, more surface active since they become slow on lower and lower size that one. Now you can able to see here and next to come to the point here, you can see this one. The color, shape, size, there's no categorization. They can have all kinds of sizes, and then they can have all kinds of colors. They can have all kinds of shapes. And this is a major issue for us to detect them in the from environmental samples. Now come to the point where they are going. When we throw a plastic, waste plastic, where they are going. So you can say that one again, you can see this, the total, and finally they are reaching to the oceans. From oceans where they are going, again, there are some of these micro and nanoplastics are getting sedimented in the ocean, but major portion, they are returning to our homes in terms of food, in terms of water, and in other terms. Again, they are returning to means, so where they are going. So if you are throwing a bag, a waste plastic, where it's reaching finally means that final destination is again our homes. Okay. This is a major issue now. We need to be consider. It's a very serious concern. We need to consider about that things. Now come to the point here. I would like to share few things, how much percentages of plastics, how much plastic our daily life, particularly from our daily life, we are throwing our waste plastic into the environment. Here you can see that when the major portion from our homes only. The 35% of synthetic textiles, 24% of the city dust, and then vehicle tires from 28% from vehicles. Tires only, not plastics made from plastic things. The major portion, this is really major concern is particularly in the tire. Those are the direct, we can say that one, since we have the primary and secondary microplastics, we can consider we are producing every day while we are using vehicles, we are synthesizing microplastics and throwing direct away into the environment. And consider is our vehicles are the primary sources for the micro and nanoplastics. Now you can see this one. There are more 800 million, 840 million residential washing machines. Sorry, the machines in worldwide. They consider that thousands, hundreds of tons they release into the environment every day, the fibers. And then vehicle tire abrasion is responsible for 28% of annual total primary microplastics entering the global marine environment directly. While raining season, this total goes straight away goes into our water bodies, from their water bodies to at that final destination, ocean, from ocean to our homes. On average, 50% of sewage sludge is produced for agriculture use in European, in North American countries. It's representing between 125 and 850 tons of microplastics per million inhabitants added directly to the agriculture soils. You can see this one sometimes. Even the well, they have the potential management systems we can say that in developed countries, in Europe and American countries, even such type of developed countries itself, they are causing to release 850 tons of microplastics into the agricultural soils. Then just think about the India. Even I can say that when best of my knowledge, we don't have even number, how much number we have. And then according to some studies, automotive types in EU, in European Union itself, they are going to release 500,000, roughly 500,000 tons per year, that vehicle type plastic wastes into the environment. And next slide. And now come here, as we discussed in our previous slide, they are not just forming a micro nanoplastics. During this process, they're absorbing in n number of elements, almost 50% of the elements from our periodic table. There are heavy metals, there are toxic elements, there are radioactive elements. These kinds of all elements being absorbed while they're forming microplastics, from plastics during this long process. So these elements being absorbed from different areas. This is another major issue. So still now we are thinking about, oh, if you can able to analyze a microplastic, that's enough. No, not at all. So making a micro nanoplastics in our lab is different from forming naturally in environment, so they can expose to anything, not only these elements, even they can expose to the microbes. Microbes easily can absorb on the plastics, particularly micro and nanoplastics, due to this surface. Here you can see that some the degradation, how they get erode of microplastic beads. You can see that when they're getting eroded when a slower process, or the getting eroded from 20 to 80%. So they're becoming a more and more surface, rough surfaces. So they're getting rough surface, which is easily can absorb elements and small microbes onto their surfaces. So this is another environmental and potential health risks we are facing from microplastics. Microplastics, we can say that, and microplastics itself, they are health risks, but they are again they're causing to the secondary risk of that our health issues by absorbing toxic elements and microbes. Now, next. So what are the health risks, the potential health risks can we get from that micro and nanoplastics? Now you can see this one. So whenever they reach to the ocean or water bodies, and then mainly the fishes as well as other aquatic animals, they consume along with the food, these microplastics also they consume. And then when the human beings consume these fishes or other aquatic animals, so they directly enter into the human body. Now, so there are three types of processes we can get contact with microplastics. One is direct inhalation from the air when we catch fire with and they catch fire in the environment, and then there is to release a lot of micro and nanoparticles in terms of smoke into the environment when we inhale that one. So easily, even on roads, when we go on roads, while we are traveling on the roads, we can able to see that when a lot of tires are abrasing every day, and we can't able to see that particle size. So we are inhaling those particles directly into our body on ingestion and contact directly to these things by with animals particularly. What kind of diseases we can offer when we get contact with microplastics? There's no limit. That's the reason we can get cancers, cardiovascular disorders, respiratory problems, but the defects, obesities, neurological disorders. Still, it's unclear. A lot of research is going on because the microplastic is not a very old thing. So nowadays is only the people getting slowly little aware about that microplastics. We can see that one, but still a research, a potential research is going on, and that the effect of microplastics on human being. Now here is another interesting point. We can able to see that one. Here in these slides, what we think that directly they are going to they are reaching to the ocean, water bodies, and they are consuming aquatic animals, and they are directly. But here you can see that one, another issue. They are not only from the water bodies, they are directly are reaching to our kitchen, which is one of the favorable food of our human beings is honey. What's the effect of that one? How they can reach to the human body and how they are going to be the microplastics affect. The microplastics not only affects the these humans, they also affects the what happens. Now we can see that the survival rate is going to decrease, the feeding rate is decreasing of the insects, and they are losing their body weight, and then they're getting immunity and detoxification, genes expression altered. This is because of these issues, their population is decreasing gradually. This is also another cause why their population is decreasing in the environment. So this causes to the disturbance of the ecosystems. And then this is a primary. And then through the honeybees, directly they are reaching to our honey, from honey to our human bodies. So we can say that when the micro and nanoplastics, they are not reaching not only from the aquatic lives and also from our honey. Next. So what exactly, there are some studies said that even these micro and nanoplastics are causes to diabetes in humans. This is not really acceptable or trustable, even believable, but some studies, they proved that because of this microplastic and nanoplastic contacts with human beings, what's going to be happen is the cells don't respond effectively to insulin and the elevated blood sugar levels. And in other studies and animal models, they said that they can trigger mitochondrial uh, dysfunction, inflammation, and oxidative stress, and get microbials got changes their DNA and RNA structures, which is contributed to the insulin resistance in human bodies, which is finally causes to the diabetics. So finally, which we are thinking that plastics are very good for our daily life, they are destroying our life, directly or indirectly. Here, how we can able to analyze these microplastics in preliminary stages. We can say that whatever the collecting samples from food or whatever it may be, the environmental samples, and then grinding them, and then collecting the solutions and density separation, filtration, digestion by using enzymes, and then some peroxides and some acids or salt or basic solutions. So then those liquefied solutions we can analyze using the microscopes or any other spectroscopic methods. These are the preliminary methods. Now, to this point, is when it comes to the responsibility. This is a major issue now we are facing. Now we know that a major source of microplastics and bioavailability and impacts we have seen now. Now what's the socio-political dynamics in point of view and potential actions we need to take that one. But there are many, being as a consultant of the chemical regulations, we have no doubt about it. We have the potential laws. There are many laws we have framed to control the plastics or plastic wastage. But the problem in India, particularly in India, it comes from our individual responsibility. This is the most important point we need to take as the reason is we have the everything, whatever we have mentioned, everything, but we can't able to stop the plastics, right? Either consuming or simply throwing in the open environment process. So it's my humble request to everyone. So we have to take the responsibility. If each one of us have to take somehow whatever we can able to reduce. So this is also purely depend on us also. This is our responsibility to now come to the last slide of this part 1. It's a microfluidic detection of pollutants. So why we need a microfluidic detection in this environment we can discuss in the part 2. But what we can able to do with microfluidics? Yes. So in nowadays, the microfluidic research is very familiar for biologists, but not much familiar for the chemists. Only if you're talking about that microfluidic research is mainly biological applications. They are using research for decades, but in nowadays, even that environmental scientists and chemists also they are showing interest on microfluidic research. Here, my aim is the people who wants to know a little about a simple basic knowledge of the microfluidics research, whoever wants to enter into the microfluidic research and what exactly industries need and particularly the point of micro and nanoplastics detection using microfluidic things. Now, so I'm going to the part 2. Please change my platform. Let me that. Yes. Thank you. Now, so what kind of outcomes we are going to get from this part 2 of this today's presentation? Is that fundamental knowledge of microfluidics for microplastics detection, microfluidic detection, microplastics using fluorescence, the impact of concentration on solvent effect and the detection of the microplastics, microfluidic and external staining as microfluidic staining as well as active staining, understanding how which is better and how they do that one. To what extent may a microfluidic detection be used to identify the microplastics? Are they really useful or not? If they're really useful, so if they've been able to replace and other sophisticated methods, that's we'll little bit to we'll discuss few points about those also. Now come to the point, our basic being as a chemist, so being a chemist, we know that if we are talking about microplastics, there are two types of properties we need to
Will
analyze.
you change the slide?
Hello?
Will you change
చేసానమ్మా
the?
చేసానమ్మా కాలేదా
Okay, okay. Aha. I think
అయిందా?
it's the last slide of first one.
No. This is different, Nana. This is part 2 of my presentation.
Oh.
That's over. The part 1 is over.
But
Right?
it is it is showing the last slide of
Oh,
first session.
one minute. Let me
Can let you change.
let me check that one.
Yes.
Oh, could you please how to share this screen sharing? Oh, thank you. Could you please help me in this regard? Where to get right. This is a part 2. Where is part 2 of mine? 3. Yes. Can you able to see this, sir? No.
Of course.
Yes, thank you.
Now it is
Yes.
changed.
Thank you. So as we discussed earlier, so the outcomes from this presentation is understanding fundamentals, few, not the all, because the microfluidic is very big subject and very in-depth subject. It's involved physics, chemistry, biology, material science, and everything. So we don't want, we as being a chemist, and particularly if you want to analyze the micro and nanoplastics, we don't need to go through all the basic concepts in that one. So what are the main important points? I will touch all these required points to in this presentation. Now come to the second slide. So as being a chemist, we know that one. These all are very familiar with this techniques. What we do that in generally, we collect the samples and we'll centrifuge. So for the concentration, we'll concentrate by centrifuge and we'll get that one by either by filtration or the centrifuge, whatever it may be, whichever method is possible for us. And then we simply analyze those with microscopes. And then we have given sophisticated analytical methods. As we know that one, we need to analyze in terms of two things. One is a physical property and second one is a chemical property. So these two are most important in analysis of the micro and nanoplastics. Now to come to the another point, then what's the role of microplastics here? This is what we need to understand, that since we have the sophisticated chemical analysis, but mainly the problem is arises from that. Come to this point. The problem is arises from that one. We can't able to. This is the can't able to do every sample using with this costly and time consuming, and we need skills. We don't have facilities wherever we want. This is a major issue, and particularly even in India, we are facing now, even for normal research, we don't get all facilities to get done characters of our compounds. So but there are common, and now come to the point. What are the common inspection or common identification process? As we discussed, so there are physical properties and there are chemical properties we need to discuss. So I can say that when this microfluidic, it comes under the detection based on their physical properties instead of the chemical property. Means microfluidics can able to detect a particles from the environmental samples by looking at their shape, size, and even color sometimes. So let's see whether it is so how extent we can able to do with these things. Now I'll come to the point. And come to the point, particularly, then what's the importance of the physical identification of this micro and nanoplastics in environment? So this is the most I can say that one. The chemical analysis is always comes in the second phase, but in the first phase, identifying the micro and nanoplastics in environment is a crucial point here. This is becoming more and more challenging in the for this scientists who are in the environmental or water pollution research. Why these are challenging to us? As we discussed in part 1, they are everywhere, and then they have all shapes, they have all colors exist in the environment, and all sizes also. So this is the major problem. So, and now we need a real-time monitoring systems, and then we need the simple monitoring and detecting techniques which we can able to set up even in tier 2 and tier 3 cities in small government institutes or government labs. Then only is it possible to the monitoring, because this is, since it is a degradation and reaching plastics into the environment, since it is a continuous process, yes, and then monitoring of the microplastics in environmental samples also, we can say that one, this is a continuous process. So since we can't able to do that, since it is a continuous process of monitoring, is more we can't able to do with expensive techniques like NMR, mass, and other techniques like the Raman spectroscopies, SEM, FEM, AFM, and other like techniques. It's not possible. So that's why we need a potential and reliable method or experimental technique to analyze and to detect, identify, or even separate the microplastics, that we can say that one is a microfluidic detection is one of the promising. I don't say that this is only the promising, but I can say that this is also is one of the promising technique. It has its own pros and cons, advantages and disadvantages. So that's why we can discuss a few about those advantages and disadvantages in coming slides. Now come to the another word in this which we are used in our topics today is fluorescence staining. Why we need fluorescence staining for the microplastics is another important point. As we know that when microplastic size and they are merged with all environmental other available in the environment, we can say in terms of anything, particles, small elements or compounds and microbes. So it's detecting them by visual, by eye, or by looking at simply looking, detecting them is very, is becoming very challenging. So that's why it's a fluorescence staining is useful for us to detect them easily, and then separating from other environmental pollutants. That's another thing. So, okay, now come to the Next slide one. So what are the microfluidic devices or technology or whatever it may be? So microfluidic devices are defined as platforms to manipulate and process fluid in micrometer scale. This is the most important point. As here we can say that one, the size as well as where we can manipulate the reaction or experiments also in the microfluidics, also in micrometer scale. So that is another advantage in the detecting analyzing of the microplastics. So reaction chamber. And now on second point, compared to the larger scales, particles will be more influenced by migration in microfluidic devices. And this may be used in the facilitated segregation and separation, right? So while since we use very narrow micrometer levels pathways to detect microplastics in the solutions. So we can say that since even our plastics and microplastics also the size in that one, so we can able to clearly see them and clearly observe them carefully. So we can easily separate from other environmental pollutants easily. This is more helpful for us. And then fluorescent detection, as we discussed in the previous slide, is another, this is, we can say that another asset as a the fluorescence staining of the microplastics is more helpful for us, more reliable to get the positive results in identification of the microplastics and quantification also. Now, what exactly the systems can give us is real-time environmental monitoring, on-site water quality testing, research and microplastic transport and degradation. So both. So we can observe the degradation, how the getting degraded, and how the water quality are changing time by time, and even we can monitor the real-time environmental monitoring systems and all. We can use for all these things, the microfluidics detection of the microplastics and nanoplastics. Now we can say that one. This is as we discussed in the previous slides, the microfluidics involved everything, and then particularly for talking, if you're talking about that materials being of the chemistry side, so there are a lot of chemistry materials, polymers, even silicon substrates, in terms of glass, everything is involved in that fabrication of the device, microfluidic device. And then when we're talking about micro channels, we need to sometimes we need to form the solutions into that channels. That is the electrical device. We use electrical driving force, pressure, centrifugal for driving forces, even the capillary forces will applicable, the physical forces will apply to get flow these solutions into this narrow channels. And then detection methods. We can use that optical microscopy, optics, and then electrochemistry, even other in situ techniques like mass, Raman, and then SEM. We can use, it depends upon that facility, how facilities we may sophisticated the facilities we can have in the lab. But even we can make the simple biosensors for that small scale labs, or even for live monitoring, the real-time monitoring of that one. This we can connect with that one. And then there are processing methods. Again, there are n number of processing methods, that is a 3D printing, and then particularly inkjet modeling, particularly for paper-based microfluidics, and then lithography, etching, hot pressing, soft lithography, printing, and laser carving, and all these things. So in this coming slides, we are going to discuss about lithography and 3D printing, and then another advanced method. In nowadays, they are using the laser carving, that is called laser ablation method. So these three methods you may be observe in the coming slides. And then most of the cases, the coming slides, they use the poly PDMS for the device fabrication. Now, this is a basic this is the basic micro fabrication method, and then the standard, we can say that, and this is a standard fabrication method. Sorry, this is a standard fabrication method for the microfluidic device. It's simple. This is, we can say that one. It looks so very basic, but it's very simple and effective. Most of the people still today, they use this method to fabricate the device in the labs, in particular in these labs. Here they use first the photoresist, whatever the design we want, that one, that design we mark on that one a silicon wafer, and we will etch that silicon wafer either using that various methods. Even we can use a chemical etching and photo developing and photo, whatever the methods we can want, we can use that one by etching. Once we match that one, we get the master print or like that one model, and then we cast a PDMS on that one. So now we will remove that one. We get that one on the cast PDMS solution when it's good, when it gets solidified, and then we get that negative mass, and then we can paste it on that one. We can fix it on that slide or software, whatever the software means previous, whatever software we want here. We can use that substrate, depends upon our requirement. So this is a basic soft lithography fabrication method of the a typical microfluidic device. Now come to the point. What are the key principles of microfluidic detection? So there are three key principles. One is laminar flow, a diffusion, dominated transport, and capillary effect, surface to volume ratio. What is laminar flow? The fluid flow in smooth parallel layers, no turbulence. This allows precise control over mixing reactions. So this is the most important, because when we are talking about the micro channels, this flowing here we can say that when this again we need to take the help of the microfluidic dynamics. Uh, Here, this macro and microfluidic dynamics is entirely different. Most of the cases is macro or scope or micro fluid flow is follows a turbulence process, but that's not useful for us to detect the microplastics or any other particles using the microfluidic detection. That's why we need to follow always and maintain laminar flow in our micro channels. And second one is diffusion dominated transport. This is also another important basic important point we need to consider while we are using these experiments. The molecules move mainly by diffusion, not convection, so which is ideal for controlled chemical reactions. And then capillary effects, surface tension, and capillary action can move fluids without pumps, especially in paper-based microfluidic. So you can say that when this capillary effects is more effective for paper-based microfluidics, but as we discussed in the previous slide, it may not effective this capillary property for that micro channels or microfluidics. So that's why we need some, most of the cases, we use some pumping systems for the macro fluidic while running the microfluidic experiments. And then another important point is surface to volume ratio. So compared to the macroscopic systems, there is an improvement in thermal and mass transfer due to the high surface to volume ratios on this device. So this is the most important point when we talk about the smaller sizes, whether it is microfluidic dynamics, whether it is nano or nanoparticles or microfluidics, whatever it may be, here the surface to volume ratio is it plays a crucial role. So because of these things, that entirely different the flow rates or what the flow systems, everything is going to be changed in that microfluidic devices. So that's why we can say that one is a totally entirely a different environment and properties, physical or chemical properties of the micro and nanoplastics in the microchannels we can observe from the macro samples. Now here is another important, we need to understand there are two numbers particularly in microfluidic analysis in this two, and there is a Reynolds number. What is this Reynolds number? What is this? We can say that one here. We can see that that's Reynolds number is given by an equation RE rho V D by mu. Here the rho is fluid density and V is a fluid average velocity, the inside pipe diameter, and fluid dynamic viscosity. Now, if you are running an experiment in a particular time, we can say that one, the fluid density is stable. We can say that one. And then diameter of the pipe is already, since we are fabricating a pre-design fabrication we are doing, so there is no change in diameter and micro viscosity of the fluid, the dynamic fluid. This also, since before entering into the microfluidic device, we will control all these concentrations of the solutions also. We can say that one for the particular reaction in a particular time. So these three parameters, the microfluidic density, inside pipe, the pipe diameter, and viscosity, they all are constant. Means we can say that when simply the total detection results, quality of detection results is purely dependent on fluid average velocity. So for that one, Mr. Reynolds, he's an Irish person, and then he has given some number how the fluids, how the fluids can flow in a long or narrow tubes. So for that he's proposed that two kinds of flows are possible. One is laminar flow and turbulent flow. So what is the laminar flow? You can see this one. A laminar flow is smooth, steady flow and layer over layer. So this is what we need for our experiments. We should achieve laminar flow in our micro channels if you want to get good results. Now come to the point, what is turbulent flow? So this, when we come to this point, when we are discussing about Reynolds number, when lower Reynolds number, so we can achieve laminar flow, and we can at higher number of that Reynolds number, we can get the turbulent flow, which is not suggestible for our experiments. Now, here you can see this one, the increasing while there's a small experiment he has done that one in his lab. That's simply he took the water tank and dye reservoir. He simply among that flow, in the flow of the water flow, he simply inject the dye and then how it happens while velocity, well flow velocity and time, based on time and velocity. Now here you can see that one laminar flow. This is a number 2300, but many of the there are a lot of disputes. Some people of 2000 and some people mention 2100, but we can say that when this is in between 2000 to 3300, if it is below the 2300, because I have taken that maximum rate as a 2300 a standard, we can say that when if it is below the 2300, then this laminar flow means we can able to achieve our microfluidic flow in channels, micro channels. We can achieve the laminar flow. And then there is 4000, and now above the 4000, we can say that one you can able to see the very clearly in the third picture. You can't able to see the proper movement of the dye in the along with the water flow. So that's why this is not good for our detection or identification of the micro and nanoplastics using the microfluidic detection. And then in between these two, 4000 and 200 and 2300 and 4000, so there is that's called a transitional force, a transitional flow. So these are the number. This is called this is most important for us. Now come to the what's the effect. Now until now we have seen that from this equation, the diameter and all these things. Now come to the another point. What's the role of the smooth of the surface, inner surface of the cube? This is also another major issue we need to address for that one. This is here. You can see that one, while increasing the roughness, the flow transforms into the turbulence flow. So that's why they simply say they have a rule. So you should maintain not only the Reynolds number the 2300, also you also should concern about that one, how smooth your surface, since it is a micro channel. So now, while while smoothing, while getting the changing materials and how, while experiments, he was able to achieve 14,000 Reynolds number. Until at 14,000 Reynolds number, he can able to achieve that laminar flow. So that's what even some other experiments later on, but even they were able to achieve the 20,000 Reynolds number also. Even means faster. We can say that one. The faster flows also you are able to achieve that laminar flow in that microfluidic canal systems. And now, what's the importance of the pressure loss during this another important point now? So that's why earlier we used that particularly when we will talk about the paper-based microfluidics, it purely depends on the capillary, and even for small basic microfluidic experiments using the water solutions. So we need to think about that pressure loss in the chambers in micro channels is also another important point here. And then you can see that pressure loss while that's well along with velocity. You can see in the graph that we can see that when the number the increasing, all of a sudden it starts to rise. That pressure loss means the pressure is considerably, significantly dropping whenever the solution transform into the turbulent transition after 2300 Reynolds number. And this is also another parameter. So that's why we need to maintain a laminar flow in our micro channels. This is most another important point is the pressure loss. So now come to the another number, that is Peclet number. So what is the Peclet number? The Peclet number, now you can able to see here in the right side corner, there are two tube systems, and there are two kinds of liquids we are entering, we are putting into that micro channels. How they are going to mix, how properly they are going to mix by diffusion. This is most important. Another important point we need to consider. So that's given by Peclet number. So what exactly the Peclet number here, denoted by LVX by D, is the characteristic length and velocity and diffusion coefficient or dispersion coefficient, D units for that one. So damage related to, and then it is oh sorry, one minute, this. So here, what exactly we need to achieve? So we need to achieve a diffusion instead of the convection. Again, the same like that turbulence, we don't want the convection here, we need a diffusion of the flow systems. So what happens if the Peclet number increases or decreases? And now what exactly, how much we need to achieve? The Peclet number should be below 1 for our experiments. What happens? What is, if it is above 1, that's called advection, that's mass transport by fluid motion. Means fluid motion is a dominant the properties of the flow of particles in the microchannels is dominant, diffusion is negligible, and then diffusion is a dominant process if it is below 1. So what happens of the mixing, design, and reaction rates and transport phenomenon? So if it is below 1, and then come to the point, when microfluidic devices, high Peclet numbers means the parallel fluid flows can travel long distances without mixing due to limited diffusion. This is the major issue. Yeah, you can able to see that one. If it is higher than 1, what's going to be happen if we enter into the two solutions into the microchannels for long time periods, they don't get diffused, or they don't get mixed together because of that higher Peclet number advection process of the, because here mass transport of fluid motion. And then design, the Peclet number is crucial for designing mixtures and other microfluidic components, and as it helps predict the necessary channel length and desired level of mixing. So when we design the microfluidic device to manufacture, then we need to consider based on that our experiment, our conditions, and how much length and channel diameter sizes and all we have to calculate based on that one. And reaction rates, it improves insight into how much the mass transfer and reaction rates deviate from ideal conditions. This is also we can get from the Peclet number by calculating this Peclet number from our reaction conditions. That one, transport phenomena, it serves as a quantitative indicator of the dominance and convective transport over diffusive transport in a given microfluidic systems. So the transport phenomena also is what we need to consider that. So these are the most important point we need to consider. Another number on Peclet number, so it should be below 1 for diffuser to achieve the diffuse. Now, till now, we have seen that the basic fabrication of the microfluidic device and some principles and some numbers. We have seen that one, and now come to the another important point: the geography of the microchannels. So there are, we can say that one, there are straight lines, so we can say, then Y-shaped and spiral shaped and serpentines, and a T-junction, cross-junction, and flow focusing, division, and micro chambers. So most of the cases for preliminary experiments for optimization, we use that straight line microchannels. We can say that one, if we use a single phase solution, we can say that the preferable is the continuous flow, but what is a droplet flow? And then if you are going to use that one, two kinds of solutions, two-phase solutions, then we prefer that droplet based design. That's the thing. And then types, then straight channel as well. And then what's the advantages of this channels? We can say that one, instead of that continuous flow, continuous straight line microchannels, we can say the spiral or this curved microchannels are good for our microplastic detection because they can entrap into that curves of that narrow curves of that microchannels. So, and then white channel and designed to two channels is converting primarily used to separating different components and fluid T-junction. A main channel intersects a perpendicular side channel commonly used to generate droplets. And then cross junction, two channels meet a main channel symmetrically, often in low focusing configuration to create droplets. And a spiral channel and one more is important point that one is spiral channels is good for the microplastic detection because based on size, weight, and shape. On the next slide, mixing. So why this is important? So as we see in that here, so the mixing of two solutions when we entered into the micro channels is mixing process is the most important point. So they are what kind of mixing we have that one, we have passive mixing and active mixing. So what we need to achieve that, as we discussed earlier, we need to achieve diffusion type of mixing instead of that advection type of mixing. That's we don't want that one. So that's we need to, because only where if you want to do the staining as well as that identification, we should achieve the diffusion based of that mixing. So that's why the mixing is the most important point in microfluidics. There are two types of mass, this common passive mixing and active mixing. The passive mixing is rely on specifically designed micro channel geometries to increase contact area and time between flowing samples, so passively enhancing diffusion. I can say that one is not possible in all cases. So in most of the cases, we use that active mixing. For this to achieve this active mixing, we use the external energy sources such as acoustic waves, electric fields, or magnetic fields. There are n number of methods to achieve this active mixing. We have to accelerate the mixing and fluid flow and accelerate the mixing without losing our diffusion process and laminar flow systems. Here, we know that one limitation and then intersecting channels, zigzag channels, 3D serpentine structures, embedded barriers, slanted wells, twisted channels, grooves, style, herringbone. It's a geometry. We can say that one is a geometry is also helpful to the passive microfluidic mixture. And then another part is the surface chemistry of the inner surface chemistry of the microchannels is also have the most also the effect on the type of a fluid to achieve the diffusion or laminar flow type of these things as well as the important point. That's why to avoid these drawbacks, so we choose that active microfluidic mixture. We can use acoustic, ultrasonic, and dielectroporetic, electrokinetic, time pulse, pressure, perturbation, and magnetic, thermal, and then electrodynamic force, magneto-hydrodynamic flow, electrokinetic instability. These all methods we can able to achieve that by depends upon the experiment and our feasibility which is available in our in our lab, which whatever it is, we can choose that active microfluidic mixture method, whichever we want to, whichever we can able to apply for our these things. So now here mainly if it comes to the micro nanoplastics, we can use these three types of two types of methods of passive and active mixing in the micro channels. This particularly we can able to achieve the micro channels using various geometries. We can say the spiral and serpentine and more narrows and curves and all. We can use that one. So by natural without losing pressure loss, so we'll use the pumping system also in passive mixing systems. And now come to the second two methods. We can use that electrokinetic mixing through flow reduction. It means of electric fields and active mixing through turbulence generation by means of mechanical agitation by using that sound waves. So these three methods we can able to observe in the coming slides by detecting micro and microplastics using the microfluidic devices. And then mixing we have already discussed all this. So optimize the sample preparation and facilities rapid analysis, improve sensor performance, enhance the detection and agent interaction, supports various detection techniques. Everything is already have seen and discussed all these points in this things. So now come to the our another topic is the fluorescent dyes. What kind of fluorescent dyes we can able to use? Since we are talking about all our microplastics and nanoplastics, most of the cases they are lithophilic or hydrophobic nature, but somehow when they get erode, their surfaces, so in particularly the modified natural polymers, in modified natural polymers, we need to, that's why we need to choose the staining agent, and that is fluorescent compound. We can see that all fluorescent compounds are not suitable for the staining methods of the micro and nanoplastics in the microfluidic detection process. So among them here, the most of the researchers used these few few micro fluorescent dyes. There's a Nile red, fluorescent, and rhodamine B, and then another. Some of the researchers also used the natural micro fluorescent agent, that is curcumin. Now come to the point, the excitation and emission. Since we are talking about fluorescence, we need excitation and emission wavelengths. We can able to see this one. This Nile red is a 430 excitation and 580 nanometer emission. And then curcumin is lower. We can say that one among us is very low, as 420 to 520 excitation and emission. Fluorescent 490 to 520, and rhodamine B 440 to 625 nanometers. And come to the how effective all of these. We can say that one the Nile among this Nile red and rhodamine B and Nile red is the highly sensitive, and curcumin is moderate. Curcumin fluorescent are the moderate sensitive to their micro and nanoplastics. So that's why the most of the research people they prefer Nile red staining process. So they prefer the fluorescent for they use for staining purpose. So they use that Nile red fluorescent agent. And then what about what other properties we can able to consider about while using this while using this fluorescent agents, fluorescent agents, that one most widely they binds the hydrophobic surface wall and sustainable works of electrophoresis. Particularly they use, since it is we can say that's a polar compound, they use the electrophoresis, and fluorescent they made with surface modification plastics less effective, less selective for the plastic may need surface one. Then the rhodamine B is strong signal, good for laser particles. particularly this is one of the good when we use the laser-based signal detector systems or sensors. So the broadband is one of the is good for that one. And now come to the continuous flow systems again. Now here we will see the few cases about that continuous flow system and a droplet flow systems. Then we will learn finally which we will conclude that one. And then description of that, what is the mechanism in that explores a low Reynolds number and reason to create micro environments and reactions. So we already have seen that during the geometries of the micro channel. So it's a continuous flow system, a single phase, and then there is no everything, our microplastics and everything is staying, everything they are involved in a single phase of the solution. And then here. What are the limitations of this continuous flow band broadening and a tidal dispersion? This is another major issue. We can able to see this while we are talking about continuous flow systems. So, and then wall absorption. Yes, so wall absorption is a possible associated biological materials can absorb can form biofilms on the surfaces of the inner surfaces of the microchannels. So, and low throughput. This is also another thing. So the efficiency of the detecting the microplasticals is also going to be lesser for that continuous flow systems. But we can say that when for preliminary detection or optimization or experimental conditions, even for many cases, it include is a continuous flow system is one of the lower time consuming and most effective more effective that one. So we'll see some examples among that one, and we will understand that how effective is the continuous flow systems for microfluidic detection. Now, this is a Taylor dispersion. I'm not going to much deeper into that one. Taylor dispersion is another physical phenomena where the how the microplastic particles are embedded into that solutions, how they flow along with that microfluidic systems in the microchannel. So based on that one, so it shouldn't be broadened. We can say that when the broad band broadening is the most issue. That's why we have to control all these things points while we have to optimize all this while you are conducting the experiments of this one. And then we can say that when this is a typical experimental setup, there are two typical experimental setup of these microfluidic systems. You can see that when there are lot of it, though our micro chip is very small, this is we can say that microfluidic chip or lab on chip system. So we connected sensors and we connected computers and camera recording the video, and we'll connect the small analyzers and even pumping system, and we can cooling system also to avoid that get heating and get evaporate the microchannel fluidic systems in that one. And even to control the microfluidics by the mixing process and all these things. So we need sometimes we'll use the cooling systems also. And now come to the point here. This is another basic, another setup, that simple setup of the microfluidics, and then we use either chem. Yeah, either we use either a microscope or we'll use even other Raman spectroscopy inbuilt Raman spectroscopy. We can build inbuilt here, and then there are other methods in another chemical and analytical systems also we can connect with that one. And then the syringe, flow rate, everything we can set up, and we can do that flow experiments. We have to optimize that one. Here there are some images given below while that they detect that map various hello. Various microbes, detected from these distance. Now, this staining process. So the staining here we have seen that one. Here they use two things in that particular scenario. They use the external staining process instead of that one microfluidic staining. They use simply they have done they conduct the microplastic and they put the solution of that in hexane solution. In hexane solution, what happens is and then sorry. So they stain externally by mixing up that fluorescent agent in the iron hexane solution and the particles also. After that, they are centrifuged and they get that they mix it with 5% PVA solution. This is another important point we need to consider, that while the concentrations to achieve that higher we can say that when to achieve the high resolution of the micro signal fluorescence signals, so we need to use, sometimes we need to use that higher concentrations of the fluorescent compounds, but yeah, but that's affects that causes to the aggregation of the particles. You can see that one here. I will show you. Right, yeah, here you can able to see that one. These particles get aggregated when we use that higher concentrations of that fluorescent agents. So that's why these people use it here. Sorry, yes. These people use it here. The PVA 5% PVA solution to increase the viscosity, which can able to control the flow systems in the microchannels. We can say that when here 5% PVA, they use it as a carrier fluid. Now come to the carrier fluid for the detection of the microplastics in microchannels. Now they use it here, the laser. Yes. They use it in this particular example. They use it that laser ablation method. So what is exactly laser ablation? The laser ablation is nothing but etching. We can say that it's etching. They use the laser light, and a particular depends upon that experiment and that energy they use. Whenever do process a laser on that one on the surface of the substrate, it get sublimated. It gets sublimated. The channel grooves, because in the sub images, it able to see they have used the three types of polyethylene based and acrylic polymers, so some substrates, and PDMS based substrates. But they found that polyethylene based or glycerin based substrates are more effective in that laser ablation method. But PDMS is not much effective and compared with that one. But most of the cases we use that PDMS substrate because of that convenience of the making of processing, and easily we can able to handle that one in our labs. Now come to the point here. This is another thing. So how we can able to see the how much energy depends upon energy. Channel width, and how we can able to control. Okay, what is another example of this one? Most of the cases they use the carbon dioxide laser beams to make the channels of the microfluidic channels in the using the laser ablation method. So we can say that one even more. We have to use that 4 watts or 6.8 watts, which is much lower even when compared with that our cosmetics based cosmetology. They use it 45 to 100 watts also. They use sometimes the same laser. They use the same techniques they apply for that both things to remove. But here we are making the channels in this using that carbon dioxide based laser ablation method. Now come to this
Dr.
point.
Kiran, kindly
Please.
conclude, because the session is going to be.
Oh, okay. Please give me the 5 minutes and I will conclude that
because
one.
another resource person is waiting.
Okay. Just give me 5 minutes and then I will conclude that one. Here you can able to see that because of this one, you can able to see that very clearly. And now next to, okay, I'm going to this one. Yes, so whether we can able to categorize by size. Yes, we can able to categorize the size using this microfluidic channel. But flow rate, based on the flow rate, we can't able to detect that one. And then next to point, another method is mixing. Mixing, this is a low cost, so I'm going to skip these points. Okay, let me skip here. Let me skip. Yes, limitations. Yes, limitations has been discussed about droplet based, and then this is a droplet based method. Instead of we are using continuous flow, so we'll use here channels in different shapes of geography of channels to generate droplets. So what happens? The droplets, our microparticles, when we use the droplets mixed to solutions, this drop we can be able to see here. This is in situ Raman spectroscopy of this microchannels. You can be able to see very clearly our microplastics absorbed on surface droplets. So yes, and that we can able to categorize shape, size very clearly, and we can see that every particle with particle by particle we can able to detect, and simultaneously it is coupled with Raman spectroscopy. We can able to confirm and that says size, shape, and type everything. Yes, so microfluidics we can able to do that one. If you have any doubts, you can contact me by through email. And thank you for all. For the your college people and professors for given to me this chance to give a lecture, and we'll meet you again on 27th of this month. Thank you. I'm signing off.
Thanks to Dr. A.B.V. Kiran Kumar for root level explanation. And now the vote of thanks will be delivered by Miss Manjusri.
Okay. Hello. Good evening, madam. Am I audible to everyone?
You are audible. Yes.
Okay, ma'am. Thank you everyone for this great opportunity to deliver the vote of thanks. We are deeply grateful to Dr. A.B.V. Kiran Kumar, eminent entrepreneur and innovator, for his thought-provoking session on microfluidic chip technology for micro and nanoplastic detection. Your entrepreneurial perspective and industrial insights were truly motivating. Thanks also to our participants for making this session lively and interactive. Thank you, everyone.
Okay, then I'm going to
So,
sign off. Okay.
yeah.
Yes, thank you.
Thank you, Manjusri, for your effective vote of thanks. Sorry.
Thank you, ma'am.
So
Thank you.
let us start another session, session 4. So for regarding session 4, Dr. Samir Syed will give a presentation. So for this, Dr. M.S. Pradeep will introduce Dr. Samir Syed.
Good evening to Ananda present here. Really, welcome to everyone. At the same time, it's a kind of nice opportunity for me to introduce my Dr. Samir Syed. It's my pleasure to introduce Dr. Samir Syed, a distinguished microbiologist and specializing in the sustainable agriculture and environmental sustainability. He is currently serving as a research associate at the Northwest Institute of Eco-Environment and Resources, Chinese Academy of Sciences, at the Lanzhou, China. Dr. Syed received his PhD microbiology from Sri Venkateswara University in India in 2016. His MSc in 2009, BSc in 2007, and microbiology and allied sciences. Over the past decade, has gained extensive research experiences in both India and China, working as research scientist at DRBILS and a postdoctoral fellowship at the Nanjang Normal University and a DST SERB postdoctoral fellow at Angaru, India. His research focuses on the plant growth promoting Rhizosphere, PGPR, and biosmart nanofertilizers and soil fertility, as well as soil microbe CO2 interactions and heavy metal bioremediations. He has published widely in peer-reviewed journals with significant contributions on microbiological remediations, oxalate carbonate pathways, and sustainable bioorganic fertilizers. In recognition of his scientific contribution, Dr. Syed was awarded the prestigious DST SARB Served National Postdoctoral Fellowship by the Government of India. Along his research, he has taught as an academic consultant at Sri Venkateswara University and contributes actively to the scientific community as a member of professional societies and a reviewer and reputed international journals, including Process Biochemistry, Material Letters, and the Journal of Stored Products Research. Please join me in welcoming Dr. Samir Syed, sir. Thank you, Ananda.
Thank you, Dr. Pradeep, for your kind introduction. So, sir, Dr. Samir Syed,
you, Dr.
kindly join with us. Okay, sir.
Thanks for introduction, Dr. Pradeep sir. So thanks for the opportunity for the presentation, and welcome to the session 4. Can you able to see my screen, ma'am?
Sure, sir. Yeah, it is visible.
Okay. Yeah. So
you can continue, sir.
Yes, thank you. The topic of today's presentation and from some of my studies is we are currently working on this Halophyte-Associated Rhizosphere Microbiota, which can work as biocatalyst for microplastic degradation in saline environments. And over the past, since yesterday or so, you might be going through all, what are the different kinds of plastics and different, the reason why we use plastics in a larger scale. And just to recap from my side, so these are synthetic polymers, which are petroleum derived hydrocarbons. Because of their lightweight and durability, and because of their cost-effective production and scale, we use plastics in many of uh, our applications. And because of its chemical structure and even the physical properties, it is too tough to degrade plastics. So that makes it more resilient and also a very effective ingredient to use in multiple applications. And plastics are of two types. One has a carbon-carbon backbone plastics. For example, polyethylene, polystyrene, polypropylene, or polyvinyl chloride, which has a carbon-carbon backbone. And there are also different kinds of plastics which don't have only carbon-carbon, can also have carbon, nitrogen, or carbon oxygen. Example is PET, which is widely used. Most of our bottles are made up of PET. And to be frank, current discussion is mostly about these heteroatomic chain plastics. And the other kind of plastics in heteroatomic chain plastics is polyurethane. So the major challenge is it's more than usage of plastics. It's the degradation, and not only degradation, plastics will also leach out and will be degraded to finer particles that are lesser than 5 millimeters, which are called microplastics. That makes them ubiquitous in terrestrial and aquatic ecosystems, and that makes them even more toxic to environment. So coming to the chemical structure of plastics, as I even told that there are different kinds of plastics based on their chemical structure. So you could see the CC bond of PE, PVC, and PP and PS, and you can also have a different plastics with head will also have a CO and CnHCO backbones. So you could see the plastic types based on the size of post their leaching or degradation. You could see the primary manufactured products of the current plastics what we use, or if you say them as primary. In the process of manufacturing, there is also some degraded products, or even while using also there might be a production of secondary plastics. So the plastics can be degraded, can be characterized based on their sizes. You could see the major problem is with microplastics and nanoplastics, which get dispersed in the nature, and it's too tough to capture them, degrade them, or even recycle them. If you take megaplastics or microplastics, even mesoplastics, you can capture them and recycle them or use in nanoplastics. They get dispersed in air. The study is about how we can capture these microplastics and nanoplastics and put them for degradation. So this is to give a picture of how the global plastic crisis is. So you could see the magnitude and scale. Yeah, thanks for that. So you could see the global plastic crisis in terms of magnitude and scale, you could see that the amount of production, the plastic waste, what the world produces almost like 10 to 20 million tons, and only out of this 10 to 20 million tons, only and it will take almost 10 to 1,000 years to decompose these plastics, and so that's the magnitude where we are looking at uh, for the plastic collection and degradation. As I told even before that microplastics are defined by the size of a plastic particle. If a particle size is lesser than 5 millimeter, then we characterize them as a microplastics, which are the major bottleneck for degradation of the plastics in the current day use. So coming to the threats posed by microplastics, you could see that these microplastics accumulate in the environment, and they are extremely resistant to natural processes, and even they pose a significant threat to human health and ecosystems. The key problems include they are persistent in environmental pollution, because as I showed that any plastic is tough to degrade, so they will be persistent in environmental pollution. So they resist the natural biodegradation, and it will take centuries, 10 centuries, almost, let's say 1,000 years, for some plastics to get degraded. And as they are micro in nature, so the contamination is too tough to capture them. So approximately 60% of all plastic degraded in discarded in environment by 2017 are micro and nano sized plastic particles, and they also pose a significant health risk. They will also recently there were reports that microplastics are even detected in the human bloodstream or even the animal bloodstreams. And most of these, it's not only the microplastics that are threatful. Most we also use anti what you say agents, let's say some emulsifiers, some fire extinguishing agents in the plastics to make them to increase their properties. They also pose significant health risk. For example, bisphenols, polybrominated diethyl ethers, or polychlorinated uh, bromines, so which enters food chain and also get into the bloodstreams of human and animal lives. So coming to the challenges posed for degradation of plastics. So the first reason is for any plastic degradation to start, the ends need to be degraded first, which requires UV and oxygen. So let's say the plastics, most of them, let's say that are buried inside the soil or that are under the water, are not exposed to UV or oxygen. That makes the ends to degrade first. So the carbon-carbon backbone polymers is mainly, the degradation is mainly initiated by UV radiation, oxygen. So the plastics which are uh, not exposed to these factors get remained undegradable. So once the ends get degraded, then comes the enzymatic process. Unfortunately, we don't have enzymes that robustly degrade the plastics. Currently, there are every year since past decade, there are much research and publishing going on where people do publish some enzymes, even crystal structures getting deciphered year on year, but none of them have a high turnover number to degrade these plastics. So that makes another bottleneck for degradation of plastics. And we also don't know how these enzymes work. So there are unknown degradation mechanism. So currently the precise mechanism for degradation of covalent bonds in carbon-carbon backbone are not well understood. And there are no specific enzymes for biodegradability of high molecular weight forms that have been fully characterized. And coming to the core of the current presentation, so here I'm trying to present halophytes and their associated microbiota in the rhizosphere that might give us a chance to isolate enzymes or microorganisms that can degrade plastics. The reason why these rhizospheres and these microbiota that are associated with halophytes could have a potential enzymes for degradation of or organisms for protection degradation of for plastics is because they stay in a very harsh environment and their metabolism is mostly robust, and their adaptability or evolution is too fast. So any uh, disturbance or disparity in the micro ecosystem, they can quickly evolve. So that's the robustness what these microbiota possess that are associated with the halophyte ecosystem. So most of these halophytes, which are salt-tolerant plant species, as you all know, so mostly they exist in brackish waters, and that, as you correctly guess, they are mostly where the rivers meet the ocean, dominant salt marshes. So coming to the species in particular, you could see Abyssinia, Acanthus, or Bruguiera species, which are mostly mangroves that exist in these hotspots where exactly the rivers meet uh, oceans, and they exist in harsh saline conditions. So mangroves, as you know, they have a special futures to exist in or to evolve in a salt rich soil conditions. They have nematophores, okay, so which help them tolerate high salt. And coming to acanthus species, they also have a spiny leaves. So ideally, it's a uh, drought resistant. Feature of drought resistant species. And coming to Bruguiera species, they have a knee root formations. All these different formations help them acclimatize for the high salt conditions, uh, and not only tolerating the high salt conditions, they could also create environment for the microbiota that live in their root systems. So that is more important part which we wanted to stress on. And coming to Spartina grass, so which predominantly grow in these marshy brackish waters, salt rich waters. So, and currently we found many case studies where there are many uh, microbiomes in these Spartina root systems that have a special enzymes that could degrade plastics. So the next few slides will be mostly based on the Spartina alterniflora species and their microbiome. And there are rhizosphere, the root zone where the root zone of these halophytes. So it's a very high biodegradation hotspot where we can have a plant microbiome interface where the soil root interface hosts diverse microbial essential for host adaptation to environmental stresses, and they also possess high degradation potential. They have enhanced microbial diversity and abundance that create optimal conditions for plastic degradation. And as these plants and microbiomes uh, are in salt-rich conditions, of course, they have a high saline adaptability. So these specialized microorganisms thrive in high salt conditions while maintaining their metabolic activity. So they have a different efflux systems to maintain osmotic balance, and also the enzymes and metabolisms what these things, these microbiomes perform, it will be entirely different from normal physiological pH terrestrial systems. So they provide a good opportunity for looking for enzymes that could have a potentiality to degrade the plastics. And not only these rhizosphere also have some beneficial organisms for plant to survive as such, like nitrogen fixing rhizobium also. And coming to the rhizobiome of Spartina species, the grass, the shrubs that grow in these marshy lands. And the major dominant bacterial phyla in these halophyte rhizospheres is Proteobacteria, Bacteroidetes, and Actinobacteria. Proteobacteria, it is the most abundant phylum across halophyte species. These include Glox maritima and Salicorina, and they have a diverse metabolic capabilities and high salt tolerance, and they also have plastic degradation potential. And coming to Bacteroidetes, so they're the second dominant phylum that have specialized enzyme systems. They are known for complex carbohydrate degradation. And coming to actinobacteria, the important contributor to plastic degradation in saline environments is done by actinobacteria. It is known for their enzyme diversity, environmental persistence, and secondary metabolite production. And coming to some other case studies, so as I told, that the dominant bacteria phyla in these Spartina species and halophyte rhizosphere at large are these Proteobacteria, Bacteroidetes, and Actinobacteria. Apart from these rhizospheres also have beneficial organisms that help the plants as such. These are actinoplanes, Mariomonas, and Rhizobium. As you know, Rhizobium is mostly nitrogen-fixing bacteria that are also present in legumes. And Mariomonas, it's a marine adapter bacterium showing enhanced abundance in halophyte root zones and salt tolerance. And actinoplanes, the specialized actinobacterium enriched in Glox maritim rhizosphere with the documented polymer degrading enzyme systems. And coming to beneficial bacterial generia in marine halophytes, so these are the beneficial bacterium that are present, which I discussed. So there's another case study which is from India in Cochin backwaters. So rhizosphere sediments collected from 3 dominant mangrove species in Cochin backwaters of Kerala, India. These are Abyssinia, Macranthus, and Bulgaria. These biogeographically significant location represent a transition zone between freshwater and maritime environments, creating a unique selective pressure for microbial communities. The isolated strains from these marshy lands that are known for plastic degradation are Pristium megatherium species and Bacillus cereus and Pristium megatherium, another subtype. So these are Pristium megatherium is a gram-positive rod-shaped bacterium isolated from the rhizospheres of Abyssinia mangroves, and they are demonstrated robust growth on microplastic supplemented media with high enzyme production rates in lab conditions. And coming to Bacillus cereus, these are also gram-positive bacterium showing a broad spectrum plastic degradation capabilities. First report of this species was from mangrove rhizosphere with microplastic utilization. And usually these are the different stages of how the plastics get degraded. So the first stage is biodeterioration, where the enzyme initially destruct the microplastic surface through their oxidative and hydrolytic processes. These are oxygen-rich processes, so that require sunlight and oxygen. And then comes biofragmentation. So the secretion of specialized enzymes breaks the destructed microplastics from the surface into a smaller monomer compounds. And then comes a bioassimilation, which is the final step where the polymer gets degraded into monomer so that the carbon dioxide is released into the environment. And the major process here happens through biofilm formation by microorganisms, and in turn microbial mass grows here to produce a biomass, and the plastic get completely demineralized from a starting polymer stage to a monomer at the end. So there are different stages of microbial degradation process. As I told, the biodegradation process is the toughest thing because it requires, it's a hydrolysis that requires high UV and oxygen demand, and most of the plastics that are microplastics especially are not exposed to oxygen or UV radiation. So that is a major step. And the biofragmentation, which is enzymatic step, the current enzyme doesn't have a high turnover to degrade the plastics. The current rates of degradations, it will take almost years. So there is a high need for enzyme engineering at this step, where there is a need for robust uh, engineered enzymes that can degrade these plastics. So this is another case study which was recently published. So the enzyme here is PET6. So where it is from a Vibrio species. Okay, it is known for, I think yesterday you would have heard about Ideonella and PETase, which is another robust enzyme. So it is not as that of Ideonella PETase, but PET6 do have a significant characteristics what a PET degrading enzyme or a polymer, I mean plastic polymer degrading enzyme should have. They have a alpha beta hydrolase fold, and that are and characterized by 8 beta strand surrounded by alpha helices, and they also have a catalytic triad, which is also conserved even in PETase. They have a serine, aspartate, and histidine catalytic triad that actually degrades the backbone of most of the polymers. So the key feature of PET is the presence of a third internal disulfide bridge. Among PET hydrolases, which contribute to its adaptation to high salt environment, isolated from, as I told, the Vibrio species that are present in these halophyte rhizospheres. So coming to the key structural features, which I even narrated, so they also have a alpha beta hydrolase fold, and 8 beta strand and alpha surrounding alpha helices fold, and conserved catalytic triad, and a third disulfide bridge, which are more specific for this PET6 protein. So that this disulfide bridges and the beta strands usually makes the enzyme more structurally stable and robust to exist in these high saline environments. And not only as in the different classes of PET degrading enzymes, most of them follow more or less the same catalytic activity, and they degrade different types of plastics. So the major plastic degrading enzymes fall into these 4 different classes. One is polyethylene glycol dehydrogenases. These enzymes are specialized in targeting polyethylene glycol bonds. They are essential for processing PEG-containing polymers, commonly found in marine environments again. And the second class is esterases. They are broad-spectrum enzymes cleaving ester bonds in various plastic polymers. They are critical for polyester degradation pathways. And the lipases. And lipases are more diverse. Currently, people are using even lipases for API synthesis. So you would have heard about pregabalin or even some statins, where people use lipases for production of APIs. The same is here, where they're using it for degradation of CO bond. So lipases are versatile enzymes with activity against both natural lipids and synthetic polymers containing ester linkages. And then come cutinases, so plant cell wall degrading enzymes, which are also shown to act against PET and other synthetic polymers. So as I told previously, so even in the Cochin backwaters, we found different organisms, mostly from the mangrove rhizosphere region. The enzyme activity measurements reveal distinct metabolic specializations among the isolated strains. These organisms are known to produce the lipases, cutinases, and esterases classes of enzymes known for degrading plastics. And so each organism is known to have a different enzyme class. So Pfisteria megatherium has a robust PEG dehydrogenase synthesis, and Bacillus ceres has a potent enzyme production capability. And Pfisteria megatherium species 1MB38 also has a PEG dehydrogenase activity, but it's not as that of SXCO1. So polyethylene glycol dehydrogenase represent a specialized enzyme crucial for degrading PEG-modified plastics commonly used in marine applications. The differential production capabilities among strains demonstrate the metabolic diversity within even closely related bacterial species, showing their potential for variable bacteriological biotechnological applications. So most of the studies about either PVC degradation or how these enzymes work is done by FTR spectroscopy. So this will give the degradation products once that get degraded. So you could have a control where we can have untreated PVC showing a characteristic peaks with hydroxyl stretching at different nanometers, and also that also shows carbon chloride links at different peaks. So once you have a degradation, so then you have a different peaks altogether that can be showed by lowest wave numbers and additional peaks which are not observed in controls. So the basic idea is that we take a pre-sterilized PVC films. They were cut into standardized 2 into 2 mm fragments and incubated in sterile mineral salt media for 30 days at 25 degrees. This experimental design simulates realistic environmental conditions while allowing precise measurements for structural changes of these microplastics with bacteria together. And another way to even study the bacterial, physical, and chemical properties and their interaction with microbial consortia is SEM, scanning electron microscopy. So this analysis provides the study on how exactly the polymer is getting affected on the surface and how exactly the biofilm of the bacteria is getting produced. That actually indicates the cell-to-cell interaction and the biomass production, and also energy utilization of the bacteria from the microplastics. And also it will also give information on surface degradation. So as the biofilm production started, as the changes on the control starts, then comes the terminal stage where you can see the surface degradation, if at all there is an organism or enzyme that is getting produced from the organism has any impact on the plastics. So the PET6 enzyme, which I told, Vibrio species. So they are known for, they are actually called marine plastic gradation specialists. The genus Vibrio occupies a unique ecological niche as ubiquitous inhabitants of saline and maritime environments, where they play critical roles in carbon nitrogen cycling. Their widespread distribution and metabolic versatility position them as a key players in maritime plastic degradation. Vibrio species demonstrate remarkable adaptability to varying salinity conditions, temperature fluctuations, and nutrient availability, characteristics essential for effective bioremediation and dynamic coastal environments where plastic pollution accumulates. So the Vibrio species are known to form a biofilm. So that is a major, even if you see the major bottleneck with Vibrio cholera, which is a pathogenic organism that exists in animal species, their activity, it's too tough to regulate them because they form a biofilm. So this cooperative bacterial communities that makes them too robust to even disrupt with any antibacterials also. The same phenomena is also followed by this Vibrio species that produce PET6 enzyme. So this is the characteristics that it utilizes here for degradation of plastics. So, and it is also characteristics that it utilizes for marine adaptability for the saline, high saline environments. So coming to, as I told, that most of the enzymes that are there presently are actually having very low turnovers. Though the crystal structures are known, though the activity are getting deciphered, still they are not that much potent to know or to have potential to degrade the plastics in hours. So it will take a lot of times, or even for the existing enzymes to act in a commercial way to degrade the plastics. So the one way to enhance the processivity of the current enzymes that degrade plastics is a comparative study of them along with the extremophile enzymes which are present in harsh conditions, as currently what we are looking is the high salt conditions. The same way we also need to look at hydrothermal vents, polar ecosystems, and hypersaline environments it where it will have a scope for identifying even more robust plastic degrading enzymes, or at least knowing the structures of those enzymes for further protein engineering studies to increase the turnovers of current low turnover plastic degrading enzymes. So the research into extremophile enzymes found in diverse environments provide the foundation for novel industrial applications. The protein engineering then allows us to optimize these natural enzymes for specific tasks such as enhancing plastic processing and bioremediation. The high hydrothermal vents, most of if you take restriction enzymes that we currently operate in microbiology labs, or even the polymerases, the fusion polymerase and all, most of them are isolated from the organisms that exist in these harsh environments. So one of that harsh environment is hydrothermal vents. If you would have heard about deep vent polymerase, which is known for high processivity in PCR reactions, one of the costliest enzyme also. It's also found in some of the organisms from hydrothermal vents. That's why that name comes from. So these hydrothermal vents, there exist a deep sea extremophiles may harbor the thermostable enzymes with superior industrial applications for high temperature plastic processing. So they provide a good opportunity to look into for any plastic degrading enzymes in those areas also. Then comes the polar ecosystems. These cold tolerating organisms that are adaptable to extreme cold could provide enzymes for ambient temperatures and bioremediation process. And the hypersaline environments, which we are also looking at currently, the topic of study. Uh, but these are mostly free living organisms that exist in hypersaline environments. So mostly in coastal and maritime regions where the plastic pollution is high. So they produce, they have a really good scope to isolate organisms that are surviving on plastic as a only carbon source. So the protein engineering strategies, from the knowledge what we gain from the organisms and proteins we isolated from these extreme conditions, will actually pave way for the protein engineering strategies. So when we engineer a protein, so most of the times we use in silico studies to start with, the computational studies. So we need to increase its thermostability. For any enzyme to be commercially viable, it need to have different checkpoints. It need to be thermostable. It need to be tolerate high environment, high temperatures. It should be solvent tolerant. So it should tolerate organic solvents that people use in industries, either to solubilize the hydrophobic molecules that are byproducts of any chemical polymer. So that enzyme should also have this characteristic. It should be temperature tolerant, it should be solvent tolerant, and it should have high processivity, it should have high turnover numbers, and it should be stable. It should be stable over a longer period of time, because in industrial setups where people handle fermenters or chemical reactors at the scale of 10 lakhs, 5 lakh liters, we don't need to spend much energies to control the microenvironments or so. So enzyme need to work too robustly in those conditions to be commercially viable. So people do engineer proteins for these to impart specific characteristics into these enzymes. So the same strategies were even demonstrated, suggested here. So the reason why people do protein engineering is to improve thermostability for industrial conditions, enhance salt tolerance for maritime applications, increased catalytic efficiency, and they should also have a broader specificity. So it's not only that the enzyme works only on PETs or PUs, it should also work on, because when we collect plastics, it's not only primary CC bond or a polymer with only CC bond. We'll also have PETs, we'll also have PVCs, different kinds of plastics when we try to degrade. So the enzyme should have broad separate specificity, and also it should be resistant to product inhibition. So some of the byproducts might inhibit the enzyme. So people do engineer the residues that are susceptible for the changes upon most the allosteric enzymes, let's say. So people do mitigate the allosteric sites to prevent product inhibition. So these are the different strategies what people follow, and we assume that we should also follow the same strategies to design a robust, industrially relevant, commercially viable plastic degrading enzyme. And coming to redox chemistry and salt marsh ecosystems, halophyte environments, particularly salt marsh ecosystems, dominated by Spartina alternatifera, the salt mar, the marshes, the shrubs that are present in these marshy lands, exhibit complex redox chemistry that creates powerful selective pressure, shaping microbial community structure and function. The alternating oxidized and reduced zones with these sediments create diverse niches for specialized microbial groups, including those involved in iron and sulfur metabolism. These metabolic processes directly influence the availability of electron acceptors and donors, biodegradation pathways. So these iron oxidizing bacteria that are present in the Spartina grasses, so they need, they have a different metabolism and redox species that can transport higher oxygen, higher, the sense like uh, you would have heard about some proteins called siderophores in some organisms that can capture ferrous. Okay, so in the same way, these uh, bacteria that are harboring in the Rhizosphere spartina will also have enzymes that can transport higher oxygen concentrations. So apart from that, they also have a higher iron recycling, because iron is a chief element that hold oxygen when it comes to proteins. It acts as a cofactor for many of the enzymes, for like example hemes or cytochrome P450s. So where it's the chief cofactor there is metal ion, there is iron that hold oxygen, and these organisms that are harbored in Rhizosphere of spartina also are known to have this iron oxidizing bacteria that are shown to have uh, higher in concentration. When we compare to normal plant Rhizosphere, you can see these species, these particular enzymes to be in higher concentrations in these particular marshes. And coming to iron oxidizing bacteria, so as I told that these species have a high concentration of proteins that can sequester high oxygen and high oxygen through ferrous, and they also know to have high redox potential capabilities. So these are different uh, characterization. So spartina also exists in different forms, tall and short forms. So it is known that the tall forms, which have extensive root systems, are known to harbor diverse microbiota when we compare to the short forms, and that's what it is depicted here. So the tall spartina have, you could see that uh, uh, where the bacterial concentration in these tall Spartina is much higher than any other Spartina species that are available. So these are different, again, different sulfur reducing bacteria present in these Spartina species that form a different bacterial family, and they also have different capabilities to reduce sulfur. So you could see the different bacterial classes here, which are part of Spartina Rhizosphere. Coming to the microbial consortia for degradation, the principles, potential, and the global impact. So, uh, so as I told that here we are looking at a rhizosphere microbiota approach. It's not the single organism that does the activity here. It's a consortia. It's a consortia of different organisms that are coexisting in rhizosphere uh, that act together. So these consortium-based approaches offer significant advantages for enhanced degradation processes. So they will have synergistic effects where multi-species consortia achieve degradation rates exceeding individual strain capabilities through complementary enzymatic activities. And there are also known these consortia-based approaches where the cultures coexist. It will also provide them environmental stability, where diverse microbial communities maintain activity across varying environmental conditions, providing robust bioremediation solutions. And it will also provide them opportunity for a scalable implementation. So, because each organism will have its own capability, and the byproduct of one organism is used as a primary carbon source by another organisms. So these different organisms exist.
Sir, your voice is breaking.
Biodegradation potential for microplastic contamination. Enzymes like PET6 combined with protein sustainable biotechnological solutions for maritime plastic pollution. The future research should prioritize scaling laboratory discoveries to find applications and integrating biological solutions with existing waste management strategies. So another case study is about deep sea enzyme evolution. The deep sea environment presents extraordinary challenges, including high hydrostatic pressure, near freezing temperatures, and elevated salinity concentrations. These extreme conditions have driven the evolution of remarkable, stable, and robust enzymes with unique properties valuable for biotechnological applications. These deep sea derived enzymes often exhibit exceptional thermal stability, pressure tolerance, and salt resistance, characteristics that make them ideal candidates for industrial plastic recycling processes operating under harsh conditions. The PET6 halophilic plastic degrading enzymes, for example, exhibit these unique properties. A halophile enzyme with significant potential for plastic degradation. So PET6, as the structure is even discussed before. So here is even more detailed study which was published recently. So as I told that these are from the marine bacteria, Vibrio gasogens, commonly found in saltwater marsh mud, marine biofilms, and estuarine environments. This enzyme represents a key adaptation for plastic degradation in high salt salinity conditions. Some of the biochemical features of PET6 is PET6 has lower overall PET hydrolytic activity than other PETases like Idenella cyclonesis PETase, which was discussed yesterday, I guess. So it excels in very high salt concentrations with optimal performance around 1 to 1.5 molar NaCl. So it do require, as as exist in high salt concentrations. Its crystal structure reveals molecular features, including sodium calcium ion interactions that contributes to its stability and activity in saline conditions. It has an optimal operating temperature is about 50 degrees. That makes it more or less a qualified candidate uh, to be a industrially relevant enzyme, because operating at 50 degrees, above 50 to be frank, it's a good condition for an enzyme to be picked for an industrial scale activity. So there is also potential for significant activity enhancement through molecular engineering. So there are different protein engineering strategies to further increase its turnovers and stabilities in organic solvents, and also increase its broader substrate specificity to make it more industrially relevant. So PET6 demonstrates optimal activity between 45 to 50 degrees, contrasting sharply with PETase, which activity its optimal activity is at 30 degrees, which is not ideal to be operated at industrial conditions, at least not in India. So this thermal adaptation reflects the enzyme's evolution in warm saline environments. So coming to the environmental relevance, the halophilic nature of PET6 makes it a valuable model for studying PET biodegradation in marine environments. It directly addresses the global plastic waste challenge in oceans. Its widespread presence in Vibrio species associated with the plastisphere highlights its ecological significance. It shows much potential for environmental bioremediation. And the PET6 structure and its significance. So the significance of structure is that it has a different structural motifs and characteristics that makes this enzyme more salt tolerant. The presence of additional disulfide bond in the N terminal provides structural insights into PET6 stability to function effectively at very high salt concentrations. And the substrate interaction through these triad, the three-dimensional structure, particularly the presence of tyrosine 248 residue, creates a binding groove that is distinct from other petases, suggesting a different substrate binding mechanism. So that makes this enzyme more relevant compared to any other petases that are existing currently. And it also has a similarities with the existing petases, so or hydrolyses, such as a unique disulfide bridge or catalytic triad or beta alpha helices hydrolyze fold. So there are the different features that makes it on par comparable with the existing petases, and also it also has a different broader spectrum. And this is a comparison structurally with comparison with PET6 and Idonella's petase. So you could see here a PET6 crystal structure with the three protein molecules, including a phosphate, sodium, and chloride ions. So, and the catalytic triad depicted here in form of ball and stick. So it's a serine histidine aspartate. It's highlighted in the pink, along with three labeled disulfide bonds. And when we superimpose the structures of PET6 and PETase, both the crystal structures which are deciphered, it's not modeled through any alpha fold or so, whose structures are deciphered through extra diffraction. When you superimpose these structures, the only deviations happen in the minor in the loops and the terminus. So that shows how well the conserved the enzymatic architecture in the degradation of these plastic polymers. So the ion binding in PET6 involves two sodium ions coordinated by carbonyl oxygens and water molecules, and chloride in a smaller pocket. The key structural features are the positions of the dark orange loop here. So, and the two residues of the double mutant near the active site. So the overall the point here is that there are different hotspots for mutations, and there are also conserved residues which need not to be touched for improving the activity. So these conserved residues are almost similar in structure when we compared with PET6 and PETase. And there are different hotspots for mutations which can be mutated to increase its stability further, and tolerance for organic solvents also, to make it more robust, industrially relevant enzyme. And coming to the molecular adaptations, as I told, that the crystal structure have ion binding sites. So it has a mostly monovalent preference. So it is bound to sodium ions and chloride ion. Compared, most of the enzymes that exist currently use divalent cations like calcium, magnesium, manganese. So most of them use divalent cations for catalytic functions. The strange feature is that these enzymes are bound by sodium and chloride ions that make them more evolutionary in the salt environment preferences. And these ion binding sites also provides crucial protein stabilization and directly promotes catalytic activity under high salt conditions. And it also have a when we compare the substrate binding group of PET6 and PETase, the structural analysis reveal subtle but critical differences between PET6 and PETase binding sites. While both enzymes share the characteristic alpha beta hydrolase fold, their substrate interaction mechanisms differ significantly. PETase exhibits a distinct shallow binding groove optimized for L-shaped substrate binding, while PET6 binding sites include a blocking knob that restricts the traditional L-binding mode. This structural difference directly impacts catalytic efficiency and substrate specificity. The blocking knob, which is specific for PET6 binding site, is have a tyrosine 248 residue. So this tyrosine 248 residue create a physical obstruction in PET6 substrate binding groove, limiting traditional L-shaped binding mode which these petases have. So corresponding position in this blocking knob in petase is occupied by a more smaller asparagine residue, allowing unobstructed substrate access. So the overall key point which I need to draw is that so this depicts that PETase has a broader specificity for the substrates. It is known to work on petases, which is very much deciphered, and it can cleave larger polymers in the sense like oligomers. That is not the case with PET6, which has a obstruction because of these tyrosine 248 residue. So it need to have a polymers need to be further fragmented to uh, very smaller oligomer structure to be catalytically active. So that is a major bottleneck which need to be addressed by protein engineering studies to make it more industrially robust. So though it has a different, a good temperature tolerance and salt environment tolerance, it falls short of its basic catalytic activity in binding to substrates that are larger, which is a characteristic of many of these polymers. So these need to be engineered to make it more relevant for the current industrial strategies to degrade plastics. So the engineering target obviously is like a tyrosine 248 position. It's identified for protein engineering studies to improve further substrate variability also. So there was a protein, PET6 variant where protein engineering studies could successfully mutate two amino acid positions, valine to tyrosine, valine to tyrosine in 91 position and serine to alanine in 92 position. This engineered enzyme demonstrated remarkable performance improvements under optimal conditions. At 50 degrees, 1 molar NaCl, PET6 VSTA outperforms wild-type PET6 by 58% and shows 1.6-fold higher product release compared to PETase. So these improvements validate the engineering approach and highlight the potential for further optimization. So and here are some of the parameters what they used for molecular dynamic simulations, where they have done a binding mode analysis. So they gave parameters for simulations, so that how exactly each binding sites and the variants differ at different salt concentrations, and they also give it thresholds like Tanimoto coefficients indicating higher indicating enhanced binding specificities, and different hydrophobic contacts optimizing substrate positions. So these are different strategies they followed in engineering PET6 to PET6 VSTA, that is known to outperform PETase by almost like 58% fold. Sorry, outperforms PETase by 1.6%, 1.6 folds when we compare it with Adenella PETase. So these are different parameters they considered in optimizing or choosing the sites and mutating them while mutating PET6 to PET6 VSTA. One is hydroxyl pi interactions. The tyrosine 96 hydroxyl group interacts with terephthalate 5 systems at 3.5 angstrom distance, providing favorable binding energy. This is one of the sites they choose as per the as per the binding energy coefficients, and also the hydrophobic contacts and optimal alignment, which they choose in picking up the sites to modify in PET6. So another case study which I wanted to draw is the bioremediation. So apart from utilizing the existing microplastics uh, to a simpler, degrading microplastics to simpler molecules. And another advantage it provides is the bioremediation. So there's a global challenge where there's a worldwide microplastic contamination requires innovative challenges. The scale of pollution demands efficient and sustainable remediation strategies, and these halophyte-associated microorganisms offer scalable bioremediation approaches, utilizing their natural ability to degrade pollutants in diverse environments. And there is also, and we can't rely on these naturally existing enzymes in that are isolated from these habitats. We need to further look for the novel enzymes from these extreme environments like hydrothermal vents, polar ecosystems, and hypersaline environments to further engineer the enzyme and make it more available, reliable for industrial scale. Am I audible, ma'am?
Yes, sir.
Yeah. I conclude my presentation, ma'am. If anyone have any comments to make, yeah, thank you.
You can conclude, sir.
Yeah, I conclude. Yeah, so the microplastics do provide, do possess a major global challenge, and we need to engineer the current existing enzymes that are isolated from the rhizosphere of halophytes further to make it more industrially relevant. And the options we need to look at is for protein engineering is we need to have a reference enzymes from organisms that are growing in extreme conditions like hydrothermal vents, polar ecosystems, and hypersaline environments. We need to draw some conclusions from these enzymes operating in these organisms that are dwell in these ecosystems. So, and we need to use those knowledge to engineer the currently available PETAs or PET6 further to make it more industrially relevant. Yeah, thank you.
Thank you, sir, for a pleasant presentation at this evening. I hope your presentation may enjoy with the participants. So here are some queries. If possible, kindly clarify. May I ask questions, sir?
Yes, yes.
So let me ask. How do you supplement growth medium with the microplastic for these plastic degrading bacteria? What is the source of this microplastic?
So most of the current organisms use PETAs to start with. We start with PETAs, okay, and we degrade them into almost nanocrystalline forms, and that we use as a source of to make them use a source of energy along with micronutrients. So we don't supplement any energy source other than these microcrystalline plastic forms along with micronutrients.
Okay. One more question, sir. So bacterial growth is very sensitive to contamination. How the microplastic in real contaminated samples can be degraded using them?
We need to sterilize the microorganisms. We have different solvents to sterilize any form of microplastics. Like people use to start with hypo. Okay, so hypo serves as a very good material, and mercury chloride and so on. So there are different solvents. It's not autoclaving also, but we need to sterilize them with different solvents initially, then wash with microfilter. I mean milky water that is passed through 0.2 micron filters that is devoid of any bacteria also. So that will make them these microplastics contamination free. And when you start with organism, we need to start with single colony. So that single colony will decipher. I mean, from there we will know its morphology and all. Then once we conclude that this is the organism of our choice, and if you are very confident, then go for 16S RNA sequencing. That will even more further establish the organism phenotype or organism genus also. So that is how we go step by step.
Okay. So what was the growth medium for isolating Pristia, which was shown in one of the slides?
Okay, so these are some of the studies uh, I presented from the references. These are not done by me entirely, so I'm not in a position to exactly decipher like what exactly was used as such. But it would be more or less same for most of the microorganisms for used for degrading bacteria. I mean plastics.
Okay. Does salt contains microplastics?
Could be, yes. So it depends upon where you isolate the salt from.
Okay. How
So
they
let's
are
say
affecting agricultural soils, if it is there?
that is a very good question. Okay, so I'm not sure like what all studies went, how exactly these microplastics affect agriculture as such, but definitely I'm sure that they will affect the absorption of ions. So, as I told that there are different siderophores, uh, like nematophores, even for mangroves. So those get definitely inhibited, and more than microplastics as such, microplastics accumulate or attract many other ions to its surfaces. So those are the major bottlenecks. It's not microplastics as such, but it's microplastics chemical nature to attract many ions because of their surface, that will create the ionic imbalance. So that makes absorption of micronutrients too tough or erratic for agricultural crops. Micronutrients are the basic requirements for any good plant growth and metabolism. So definitely microplastics, prima facie, I can say that it is affecting the ion transport majorly.
One more from my side.
Yeah.
These ions are influenced heavy metals in the soils. That means to increase the concentration of heavy metals.
Yes, ma'am. Yeah, there is good chance that there could be a issue of biomagnification because of accumulation of heavy metals through these microplastics. So yeah, there could be a good chance.
Okay.
I'm not aware of this
Thank-
fact, ma'am, but prima facie I can say that yes, it can interfere there.
Because we worked regarding heavy metals in the soils. So that's why I asked this
Yes,
question.
yes, there might be a good chance. Yeah.
So thank you, sir. Let us invite our faculty member, Mr. J. Dixit Kumar, for a vote of thanks to Dr. Samir Syed.
Yeah, ma'am. Am I audible?
Sir? Yeah.
Yes, yes.
Hello. Am I
Yeah,
audible, ma'am?
you're audible.
Yeah, audible, sir. Audible.
So I'm Dikshit, sir, Assistant Professor, KPRIT, COE. And our sincere thanks to Dr. Samir Syed, Assistant Professor, Chinese Academy of Sciences, for his engaging presentation on Halophyte-Associated Rhizosphere Microbiota in Microplastic Biodegradation. The way you blended ecology and technology was truly inspiring, sir. A special thanks to our participants for their presence and attention. Thank you. Thank you very much. Thank you, ma'am.
So thank you for your wonderful vote of thanks. So I hope all the participants enjoyed the two sessions, both sessions. Let us have a snap from the participant side. Just mute the mics and unmute the video. Let us have a snap. Let us have a snap. Kindly unmute the videos. Dear participants, kindly unmute the videos.
Sir,
Let
can
us
you
have a snap. Principal sir.
Shamir sir, can you please stop sharing the screen?
Yeah. Thank you, one and all. So let us meet tomorrow by evening 6 o'clock. And please fill the feedback form for session 4. Now you may leave the session.
Yeah, thank you.